Good morning, good afternoon. Welcome to the very first lecture in the IEEE Instrumentation and Measurement Society Virtual Distinguished Lecture Webinar Series. I would like to introduce our speaker for today. Dr. Mihaela Albu is a professor of electrical engineering at Polytechnica University of Bucharest. She also graduated and received her PhD degree from that same university. Dr. Albu is a senior member of the IEEE and a member of the IEEE IMS TC39, which is Instrumentation for the Power Systems. She teaches courses on electrical measurements, signal processing, and smart grid topics at both graduate and undergraduate levels. Her research interests encompass synchronized measurements for wide area measurement and control systems, smart metering, DC and hybrid microgrids, power quality, IEEE and IEC standards in power. She has been PI of more than 40 research projects funded by national and international research agencies on measurements in smart grids topics. And now, without further ado, I introduce Mihaela Albu. Mihaela, the microphone is yours.
Thank you very much, Judy, for the introduction. Good afternoon, everyone. As you see, I am using the time reference associated with the geographical location, which means that I am in the laboratory in the Polytechnic University of Bucharest, not surrounded by students or colleagues, surrounded only by PNUs. So I will share my screen now, and I hope that you will see. If there is any interruption of the connection, please make us aware to overcome this. So you might ask why this topic, and actually recent changes in the power grid structure and functionality need to be addressed also from a measurement perspective. And here we'll focus among all synchronized measurements to those provided by the PNUs. So this webinar will focus on one side, on the way the measurements are performed for the control of electric power systems. And on the other side, on the PNUs as seen through the lens of their features. And among their features, we'll look more into the high reporting rate, on the model they use, and on the fact that actually they are an information concentrator, or they use an information concentrator. And in the end, with some applications most used nowadays for PMUs. So actually, why measurements are so important in electric power systems? They are important everywhere, actually. And we have to recall that power systems are critical infrastructure. And the traditional operation for more than 100 years that I try to depict in this figure was actually relying on the electricity transfer from the bulk generation to the end users via the high voltage transmission lines, then the power transformer, then the well-known distribution grid. And the real-time control, and here when I use the word control, actually is not perfectly fitting the wording in the power engineering area. It's more than that, it's taking action. So real-time taking action meant to adapt the generation to the load, and this because it was no electricity storage considered or available. How was done lately, let's say for the past 30-40 years, evolved SCADA with time constants in the order of seconds was perfectly fit for the job. So the measurements that they were providing information to the to SCADA and to all the control systems were usually the voltages, the currents, the active power, then also the reactive power. So what changed so much that we have to look also to the measurements and to see how they answer to these changes. First of all, we became greedy, and we started to exploit, or we wanted to exploit also the locally available resources. Hopefully, most of them are renewables, and unfortunately, they are intermittent. So then, because these are available at low powers, they were injected into the distribution grid. This became active, as we see. Even more, we started to operate this equilibrium between the generation and the load at less and less wider areas, and started to form local energy communities. But the most dramatical change was the fact that in all nodes of this new evolving or emerging power grid, we use for mediating the electricity transfer the static power converters. And this resulted in less inertia, or in a faster inertial response, and resulted in a time. We speak a lot about the time today, in the order of time for the control in the order of milliseconds. Today, there are in the codes of operation in Europe, for instance, 100 of milliseconds up to 200 milliseconds nominated as largest time reaction for frequency control, for instance. So moreover, the geographically decoupled phenomena revealed something very interesting, and this is not yet accepted or understood in a power system, at least for current operation, that frequency, which was for more than 100 years the system quantity, well, is not anymore this ubiquitous provider of information in a power system. Last but not least, can appear new phenomena like reverse power flow, and these ask for new control. So it might be worth to take a look to the measurement paradigm in power systems. And we all know that measurement is a bridge between the empirical and the symbolical worlds. We all know the measurement is normally a goal-driven process, and as already said, goal is not necessarily control, and can also be gathering information for modifying the models. And also we know that prior to make a measurement, we have to identify the measurement context. And this is based on the measurand. So what we have to measure, to define as well as possible, then to derive a measurement system as appropriate as possible. And of course, to identify the environment. And here started to be a problem. And I'd like to quote from the first chapter of the book, Modern Measurements, Fundamentals and Applications, edited and coordinated by Professor Ferrero, where it is stated that although only a limited number of environmental properties may influence the measurement system significantly. So it's a limited number, which means that these influence properties can be ultimately controlled and even kept constant within a given tolerance. However, there is something that cannot be controlled, no control, neither kept constant, and this is time. However, from what we spoke now, there is no trace of time, so where to look for it? And At this point, it's good also to recall what we also know, that measurement result is meaningful only when the quality is, of the measurement process is quantified. And usually we quantify following the rules, for instance, of expression the uncertainty in measurement by this standard measurement uncertainty associated with a measurement chain or measurement equipment. Here is depicted with UE from the equipment. But we saw that measurement takes time because it's a process, and we saw that we might encounter a difference between the model of the that you use for the measurement and the reality, or at least the model that we use for controlling and the control that is using the measurement. And let's call this this deviation model uncertainty. And here depicted with UM. Here is the time actually embedded. So if we go a little bit further in analyzing the measurement in electric power systems, we saw that we have to take care on what the goal is describing as and is using as an assumption. And we also know that for steady state operation, most quantities are periodical, considered periodical, and even more with sinusoidal variation. This would not be a drama, but this means that from the whole realm of signals that might carry the information from the system that we want, from the power system that we want to investigate and ultimately to control, we concentrate and we assume that we deal only with these periodical signals. How much is the error that we do, or how much is this assumption far away from the reality? We have to not necessarily to find out, because sometimes we cannot find out, but at least to think about. Now it's speaking again on the measurement. It might be useful to make a discrimination between the so-called instantaneous values and integral quantities, because it's a language abuse that we use instead of values also instantaneous quantities, and might be good to think about, because this is in my mind the reason for many misunderstandings, including in the use of PMUs, to take a look to one of the quantities essentially in the power system, which is active power, which by definition is an integral quantity. By definition cannot accept instantaneous value. Yes, instantaneous power, active power, yes, but I'm speaking about this active power, because it's requiring a time interval to be defined. Usually this time interval is multiple of the fundamental period of the signals. And then, like, copying this idea, or maybe trying to overcome difficulties in working simultaneously with integral quantities and quantities that and signals that can admit instantaneous values, like these analog signals here. People in power system preferred to use to use algorithms to obtain time series. Time series of voltage, RMS voltage, for instance, RMS current, similar to a kind of time series of active powers. The idea is to take a look if the way that these are obtained is using the same time interval. Now, the dominance of numerical measurements for achieving digital control, we are in the digital world right now, makes us operate with data instead of information, which is not wrong per se, but But remember, it is an analog system that we want to control and we want to describe and then control with such data. Therefore, it's important to check not only data integrity, and this is a kind of buzzword for the PMU area. So we have to take a look not only to these samples, yeah, the data that we obtain, and we have to take a look to the Shannon theorem, of course, because it's digitalization. This is nothing new, but to consider that is always a finite duration of the analyzed signal. So we have to choose the appropriate signal processing windows or time windows to avoid distortion in time domain, which means that Shannon theorem and the measurement time windows are equally important here. Speaking about this, way of coping with analog signals and trying to obtain time series in a kind of avant la lettre digitalization. We also we can take a look to the fact that periodic signals can be represented and are represented by only a few parameters. Let's call them information concentrators. And they are amplitude, mean value, average value, root mean square updated every half period, form factor. These are not only quantities that we encounter in the power quality area, they escaped from the power quality. If we look, again, I gave the example of the codes that govern the electricity transfer and all systems in Europe, all power systems in Europe, they refer to those definitions when you speak about voltage. So it's a kind of standard of obtaining some information compression. Unfortunately, when the waveforms are not periodical or not sinusoidal sometimes, this is a lossy information compression. This might be enough, yeah, to conclude that the choice and the choice of the measurement is not an easy task. When we want to fulfill both the duty of the measurement person or the measurement system and the duty of the one who uses this information in power system, the control, let's say. But the story does not stop here, because there is a further information loss, because again, copying a kind of analog way of data compression, the result of the measurements are not made available as they are, even if they are in the form of information concentrators or sample values, but usually, as we saw as information concentrators, there is performed further decimation of the measurement results using a known, fortunately, or unknown filter in order to achieve lower reporting rates of those measurement results. As you see, I use this term reporting rate from the PMU realm. So this is not equivalent to introducing more semantic noise as depicted by Harold Kirkham in a report of PNNL, or a model uncertainty. This is actually adding errors and is a source of errors, because it's again using a second order filter in case that is known to obtain an information compression. So we can conclude that the measurement paradigm in power system is sometimes hidden, sometimes obvious, but always data compression with a lot of information loss. Here is just a small example. it's all gained from the power quality realm. What does it mean, data aggregation, and how to obtain this decimation of measurement row of data, I mean measurement results, by using a quadratic average over some specified intervals. And here are depicted actually the intervals meant for the 50 Hertz systems. So again, from the phenomena that we want to oversee and the measurement, there are a lot of steps which have nothing to do with the measurement, but with acquiring knowledge on the expense of gathering as few numbers as possible, which actually is the task of another field. It's not a task of measurements, it's information and data compression. So you might ask why? Well, first answer is actually the message by aggregation becomes less sensitive to the measurement. So this term into the standard uncertainty, into the measurement uncertainty is becoming lower. However, it's inflating this model uncertainty because the difference between the assumed model and the reality is getting bigger with this type of decimation. Still, why? Well, it's a very easy answer, because if we consider a waveform and point of waveform measurement sampled by 150 kilohertz. This is not an unusual sampling rate. For instance, it is used by the micro PMUs. For 1 minute, one channel, one quantity, one measurement, this results in 120 megabyte, while acquiring the RMS values and performing an aggregation over 3 seconds is required for the same channel 40 bytes. And I assumed 2 bytes per data, per result. So with this, tiny introduction, we can move to the case of Phasor measurement units. And as you see here, I collected only a few of the keywords that are very much connected, tied to the Phasor measurement units. And I will not insist on each of these keywords, but I cannot escape mentioning the North American Synchrophasor Initiative, where, by the way, the experts are organizing several very interesting webinars on the various aspects of the use of PMUs. Sometimes also on the measurement side of the PMUs. I cannot also skip the here depicted with black, because this is the new logo, the IEEE Standard Association, which was actually for the first time issuing a standard that is the birth certificate of the PMU 95. I cannot skip with, I'm really happy to see and to underline that one of the first dual logo standards, IEC and IEEE, is this standard appeared in the last month of 2018, also on defining the PMU. And we can see also keywords related to synchrophasor, to symmetrical components, which was very much linked in the beginning with the PMUs, with the sampling rate, reporting rate. As said, I was borrowing already in, as an expression, timestamp, rate of change of frequency. And I did not say also frequency, but it's like opening the eyes of the power system operation, this new quantity, that has not yet a definition in the electropedia, rate of change of frequency. We have also open PMU and so on. But because we started from the measurement, we see, and I think that it was a lot of misunderstanding already for that. We see that the phasor, it's in the name of the phasor measurement unit, and we know that it's a complex equivalent in polar or rectangular form of a sinusoidal wave quantity. Well, it's not that that simple, because it's very nice highlighted the history of phasor in the first issue of Power and Energy magazine this year, made by Harold Kirkham. But more subject of misunderstanding might be the word of synchrophasor. Although this is considered related to the same phasor, but made available and calculated from information using as time reference and time signal reference for the measurement. Now, I would not repeat what is a phasor measurement unit, because we know that measures and reports synchronize the phasors and other quantities. And these and other quantities are of high interest, because we use frequency without having frequency measured with the highest resolution and accuracy today in normal, let's say, operation of power systems. It's about 1 microhertz, and the rate of change of frequency. So without these quantities, we might not see deployment of PMUs as large as we see today. But the most important is that the PMUs are using a signal model. And that signal model is embedded into the definition of the PMU, as embedded into the standard, and is not like other measurement equipment, which are defined up to a very general level, and only after that the quality is let's say, associated with the measurement equipment. It's a kind of unique decision to have the PMU embedding also a lot of from the signal model. Phasor data concentrator, it's another unit. It's not necessarily part of what we are interested in, because as the name said, is data concentrator. So is after the measurement, it's already processing the data. So the most important thing when we speak about phasor measurement unit, and when we start the case, is that is again a measurement equipment that is using information compression from usually 10 kilosamples per second, if this is the sampling frequency. Again, there are units that use higher sampling frequency to down to 50 frames or 100 frames. Again, the example is for the 50 hertz system. Now, the question is this information compression, how lossy it is? And we will see that without putting action on the existing model, it is a lossy information compression. And this has to be known by the ones that will use the measurement results. In short, the algorithm, or the way the measurements are formed, or the measurement results is formed, is that at each reporting time, and this is a multiple of 10 milliseconds in case of the 50 hertz system. One has to calculate, estimate actually the RMS value and of the signal assumed periodical, and also the time difference towards to the last peak. But as we know, the phase needs also the frequency, because it's 2 pi f delta t. We need also this very well or very accurate frequency measurement in order to derive the phase. Now, from a measurement, very practical measurement perspective, the question is, well, how many channels, where to use it? And here you see some pictures from the lab. So they are around me. I just made the pictures because it's difficult to make a video. And we can see that we can have PMUs with a standard 3-phase voltage channel, 3-phase current channel, or PMUs much more complicated, like this one that has 2 separate 3-phase voltage channels and up to 8 configurable separate 3-phase current channels, which made them suitable for measurements in substation with double bus bars and more lines. But also, I did not pronounce before, we can see a micro PMU, which means that has some similarities with the PMU, but the main difference, and this is what from a practical again point of view, is the fact that the measurement channel and measurement chain is already provided, because it's including the instrument transformers for this for performing the measurements. So the micro PMU dedicated to lower voltages, so usually to the distribution grids. The other PMUs, they need, in most cases, because they are installed in substations, they need a connection from the instrument transformers, and this means that they have to be compliant with the available burden of the measurement core of the instrument transformer. What you also see here is a live measurement from one of the PMUs in our lab, where we can see the phase voltages and one current. The other 2 currents are 0 because we have nothing connected. As we see, the frequency is lower than 50 hertz, or it was when we had this measurement. Also depicted here, and not necessarily related to the number of channels, but we'll see soon related to the difficulty of calculating the overall quality of the measurement chain, is the way that PMUs are stamped with the quality in the sense that we are used in the measurement world, and this is the total vector error. I will speak a little bit later on this difficulty, on the way that this is defined. For the moment, I would like to show some of the measurements that we analyzed, we obtained by deploying the PMUs in our lab and outside in the distribution and transmission grids, because the PMUs from very practical way can be standalone, can be moved so they can be connected in any node where the permission is granted, or they can be fixed like actually is done for most of the power systems. So we are fortunate that we have this set of PMUs where we can which can be installed in various nodes. And what we see here is the feature of having time-stamped information. So the reported measurements are also time-stamped, not only obtained based on time controlled signals, and they are obtained in 5 different locations with 5 different PMUs at 5 different voltage levels in the system. And we can see this almost synchronous variation with less than 10 millihertz of the results. And this is possible to analyze only if we have this timestamp. Again, it's not necessary to be online and fast communication. It's post-processing analysis. Also, we benefit a lot from the high reporting rate, although as seen, ideally we would need a point of wave, and there are a lot of initiatives to embed into the PMUs also measurement results including point of wave. Actually, in the micro PMUs, this is already done for finite time intervals. This is a very new analysis of an event in Romanian power systems, where we could see that following some loss of large thermal units, so it was a cascading effect, then lightning strike. So within about 4 seconds, there were lost 1,000 megawatts, which meant at that time about 20% of the load. Why saying that this high reporting rate was important is that these events, I mean, the frequency variation showed higher sensitivity to the event, to the generation loss for 2 of the nodes, while the most distant in geographical terms this time, one showed much less variation. Practically did not record these events. The green one that we see here, that also is sensitive to some of these frequency variations due to the huge power loss, is the nuclear power plant. And this shows also the robustness of the control in the power system. But this is not enough. It was a lucky situation, we can say, because we also performed measurements in the system where no conclusions could have been derived, like we saw a little bit earlier. And this is because events can result in, as we all know, in phase jump, and is still debatable in not in the measurement, but let's say in the academic world, the definition of frequency and then of rate of change of frequency. As we all know, the preferred definition for the PMU is this first derivative and then corresponding the second derivative of the phase, while most of the numerical simulation, calculus, teaching is done, at least in Europe, with frequency as nominated as this tiny f within the parentheses. And of course, there are differences when when the initial phase is not constant, and might be remedies. And of course, I am happy to underline one of the papers presented at our conference, our workshop, AMPS. So we need more robust definitions, and I only can say that following the so-called experience, good and bad, of definitions in for PMUs, there are several groups in IEC, at least. I suppose that also in IEEE, but I know in IEC that try to come with definitions of frequency, time intervals on which this frequency has to be defined, and how, and of course rate of change of frequency, in order to answer to the challenges put by the new codes of operation of power systems and connecting of the generators. All this not much data when compared with the point of wave. There are still a lot of data. We all know, we all struggle. At least I have information from a lot of companies that they cannot cope with so many data obtained despite the low reporting rate, low instead of point of wave, compared. Struggling with too much data. And there are many initiatives for integrating data coming from PMU and trying to correlate the information given by PMUs with other sources of information and measurements like smart meters with high reporting rate. And I just want to highlight the use of the Phasor platform into deriving a platform dedicated to smart grids and information in power system. And this is done by the FISMEP project, is a running project led by Professor Monti at RWTH. Basically, the idea is to, in parallel, with the use of PDCs, if it's needed or not. There are a lot of works showing that it's not necessarily needed to use the phasor data concentrator approach to publish data into one of the essential elements of this Phasor platform, and this is the Orion. Now, because everyone knows how useful are PMUs in state estimation, and I would like to say that here I'm speaking only about classical state estimation and not for distribution state estimators. For those, there are much more knowledgeable people even in the audience. And I'm thinking to Professor Ponci. What I would like only to highlight is that if we consider the linear state estimator and we start to be suddenly happy, that is a very easy way of deriving the unknown quantities by using the measurements from the PMUs and the knowledge. Let's say that we are we have that knowledge on the infrastructure. So although apparently it's an easy way and is requiring a number of PMUs, the simple fact that the PMUs require also the connection of instrument transformers that are not perfect, and we have to estimate this contribution of the whole chain elements into the measurement it's giving a headache. Much worse is, of course, when we consider the hybrid state estimation. Had one of the versions of the hybrid state estimation where some of the quantities, including power flow, are derived from the measurements of the PMUs. Then another problem appears, and that is how to correlate the information given with different reporting rates. So we have on one side the active power, reactive power, even voltage measurements provided with low reporting rate, so in SCADA typology. And on the other side, we have the PMU data. One easy solution, and I saw it already applied sometimes, is to downsize the volume of information from the PMUs and apply the same type of aggregation algorithms as in the case of power quality, for instance, and obtain synchronized among all quantities information. Another way is just to pick the measurement from the PMUs when the other measurements are provided, but of course much more interesting, and we studied how to do this to refine the low reporting rate measurements until they reach the high granularity of PMUs. This is not easy. As I said, we have the instrument transformer, we have the measurement device. Unfortunately, the instrument transformer has another way of providing the quality, which means the limits of error for ratio and limits of errors for the angle, and they have to be combined. But if we manage to combine and then we look to the influence and of selecting the instrument transformers, we observe something interesting, and this might be a high incentive for using PMUs in at least in the hybrid state estimators. We see that when using a conventional state estimator with different types of instrument transformers with different accuracy, there is no significant improvement. However, if we have a hybrid estimator, then it is a significant improvement of using better instrument transformers. And this is also for the angles and the magnitude, and I let for those interested the information into the on the paper that was written mainly in the group of Elias Kyriakides, who will all miss. As already said, with linear state estimation, we need to be lucky and know the infrastructure, I mean the parameters of the network. At least in Romania, this was not the case. So we had to start a campaign of kind of deriving a Google map of the parameters, and some details on the adventure can be also seen in a paper related to the effects of parameters and measurement uncertainty. So lack of knowledge on the parameters and measurement uncertainty on the quality of the state estimator. I will close with an overview of wide area measurement systems in Romania, and where we have 15 PMUs and one central PDC with reporting rates uh, 25 frames per second, and a very recent reported registration of 3 related events of loss of power. Again, it was more than, in total, it was more than 30% of loss, more than 1,200 megawatt in events. Uncontrolled events, and then another 700 megawatt loss in a hydropower plant. In the analysis of the frequency, it's not very well seen what happened, but we can see in the analysis of rate of change of frequency, here is a detail. So the first drop, the second drop, the third event for 700 megawatt, which was resulting in a much higher rate of change of frequency. But surprise, surprise, actually before all these events and having no relation with them, much higher rate of change of frequency following an already, let's say, not yet detected event into the European system, so outside the Romanian system. So we are on the way to define the undefined. I will skip, let's say, more details, and into this wrap up, I will just want to call actually for the people who are dealing with measurements and PMUs, but mostly measurements in power systems, to look into the issues that are still to be solved, and this is how to efficiently merge the PMU measurements with data with different reporting rates, how to correlate with emerging other measurements like smart meters with 1 second reporting rate, and especially how to compress the information in a more efficient way than this analog, like even Phasor is an information compression that is not necessarily the 21st century, and how to easily quantify the measurement quality for a PMU-based measurement chain when we have the instrument transformers, and when we already saw that is needed to have to include the model uncertainty, as we saw the time. But I think that everyone is happy that PMUs have opened the discussion on defining frequency and rate of change of frequency in emerging power systems, and let's hope that we'll have these definitions as soon as possible. With this, thank you for the attention, and I think that we can open the Q&A session. So one of the questions from Ferdi regarding the micro PMU, what do you think are the features that matter? Well, because I was also thinking a lot on this, because we use micro PMUs, we use P-cubes, and we use a little bit more in number PMUs. And what matters is for us who do not use the PMUs for protection. And actually the PMUs enter very bright in the era of measurements with the M and P type, but also as application. So in the measurement era or side of PMUs, is not critical the obtaining of the information, how fast the information arrives. Therefore, having available the data already stored into the micro PMU is a very good feature. So independent on the communication channels, independent on the availability of the storage on a server, you can have access further to this data and analysis. For the other one that I said that is important, having the instrument transformer incorporated, this was at the beginning for me a great feature because first of all, I did not have to make all these calculus for, for assessing the uncertainty of the entire channel. Now might not be number one feature because we already have the low power instrument transformers and they already appear on the market, and they can be a game changer for measurements in distribution. So this would be the answer. So if yeah, there is another question. Is there any way to specify the sampling rate of PMU, micro PMU before they are commissioned? Well, of course, it's a setting that we can select. Actually, with our PMUs, I said we travel around the distribution or transmission grids, and we install them and take data and so on. There are mobile. We have a mobile laboratory. We select depending on the case. The the reporting rate. Sorry. Now I read is the sampling rate. No, I think not. As far as I know, for micro PMUs is 25 kilohertz, and for a short time period can jump to 1 megahertz, mega samples per second. But then it's not a PMU result that we obtain, is the point of wave, is the waveform actually. For the PMUs, I also don't think that we can select. We have the 10 kilo samples per second, but maybe there are some new PMUs, or maybe the results or the products of the Open PMU initiative. There you can specify. But well, my gut is that not yet.
Do you see the question from Yuri there?
Yes, I was trying to formulate. So the question is if which is the most demanding or sensitive application that requires further increasing in the quality of energy in the distribution system. Well, for the moment, it's hard to select, because in my mind there are several issues competing for being sensitive, poor quality issues in distribution system. And when I say sensitive, means that we need also high reporting rate information, or let's say other models for the measurement, not necessarily these phasors. And I'm thinking now to the very high harmonics, so supraharmonics, those that are beyond 10 kilohertz, between 10 and 100 kilohertz, that are to be experienced with in some installations of fast charging of EVs. So this would be the most sensitive, and the second one would be the voltage variation and OLTC. So how to keep this voltage variation into the admissible band due to PV in weak PV installations in weak grids. What we experienced until now in many parts, this problem was simply put away by not giving right of connection for the PV owners or the producer that wanted to install the PV, but it's not a solution. The solution is technical, and we have to be to gather more information. Again, this means going from towards seconds, not yet milliseconds, but seconds as time. There is another high rate of change of frequency must have an effect on the long-term health and reliability of large rotating machines. If I have any statistics on the application of phasor data to assess mechanical reliability, either generation or use, and how valuable is this data to business economics? This is a great question. To be honest, I did not think to that, but I tried now to find a reason why I really did not think to this use of phasor data to assess mechanical reliability. And one answer that is in my mind is that the problem, the intensity of problems related to variability of rate of change of frequency is related to lower inertia in the system, which means that the more we have power converter mediated energy transfer, so the more we have renewables used for wind power and PV and so on for generation the electricity, the more we have the problems with rate of change of frequency, but the less we will have the sufferance of rotating machines in case of generation, because they will be displaced by other generation. However, I did not think on other types of still connected in the system of rotating machines. It's a very interesting question. Thank you, and I will pass to my colleagues, experts in electrical machines, and maybe they will find an interesting topic also to study. Thank you again.
Thank you so much, Mihaela, and thank you for sharing your expertise today. I don't see any more questions, so thank you all for attending this very first virtual distinguished lecture of the Instrumentation and Measurement Society, and I wish you all a good day. Thank you.
Thank you. Have a nice day, everyone.